All right, record in 3, rolling. Let's see what Paul Hewitt has to say about linear motion. Right now, what he's getting at there is actually a concept of like average speed. Right, if you do a total distance divided by a total time, you get like an average speed. Right? In this class, moving forward, we almost never really care about average speed. We really care a lot about instantaneous speeds. Like all of these equations on these posters in front of me are all instantaneous values. Like v naught initial velocity, that's like at an instant. Right, v final, like as your car's like rolling through the speed gates, like through the finish line, that's like an instantaneous value. If there's a cop car on the side of the road, he points a radar gun at you, says, aha, you're going 50 miles an hour now. Right? That's like an instantaneous value. That's usually what we're going to care about in this class. Okay? Instantaneous. All right, so he just turned a scalar quantity into a vector quantity. So speed is the scalar, just like how fast, right? But velocity is the vector. So it's not just how fast, which is the magnitude, but also like what direction. If that seems kind of trivial right now, it's going to be important later, right? Even in linear motion, because linear motion, suppose I want to know, I drop an object, I want to know how long does it take to hit the floor, right? But what if instead of dropping it, I throw it down so it has a starting speed, right? Well, if I throw it downwards, probably not very much time to hit the ground, but if I throw it upwards, it's still going to come back down and hit the ground, but it's going to take more time. So I need to specify the direction, and I can do that by defining either up or down as positive or negative, and you could do either way. But suppose you want gravity to be positive, so down is positive. That means if I throw it upwards, I'm throwing it into the negative direction, right? And that tells you something about maybe how long it takes. It's going to take even more time to hit the ground, right? Or what about this car in this incline, right? Now, if you release it from rest, then it just moves one direction. So it just maybe always in the forward direction. That's fine, right? What if you give it a little push? Ooh, now it's got a starting velocity. What if you give it a little push backwards up the incline and it goes backwards for a little bit and then turns around? Oh, now the direction matters. Now there's a negative direction and a positive direction, right? Okay, so there's a velocity concept, right? Velocity. Right? Hey, can you guys, this is kind of a lead into the next thing before I roll the next video. Can you guys feel velocities? Like, let's say, for example, you're a passenger in a car and your friend's driving the car and you're blindfolded. You're in the passenger seat, right? And you're on the highway. Can you tell your friend, ooh, it feels like we're going about 50 miles an hour right now. It feels like we're going about 60 miles an hour right now. Is that something you can feel? No. No is the correct answer. How about just sitting in this room? Guys, are you moving right now? You're on a giant spinning planet, about 1,000 miles an hour, right? Spinning? That's right. Yeah. But you can't feel that, right? All right. So, okay, let's go back to that. You're in a plane. You're in a plane, right? Can you guys just take a nap in a plane? You guys feel like you're sitting in this room right now? Yeah, right? So back to the car, though. There is something you can feel about that car. What can you feel in the car? Okay, besides vibration. That's true. That's true, right? Okay, turning. Actually, that was the tricky one. Right? Turning and two other things. Change of velocity. Change of velocity. Right. Change of velocity. Right. And what controls does the driver have to do that? The gas pedal and the brake, right? The gas pedal and the brake. Okay. So you're sitting in the car. If the driver slams on the gas pedal, you start to speed up. You can feel that. If he slams on the brake, you can feel that. Right? And also the steering wheel. Right? Now the steering wheel, we're not going to worry about for a few weeks. We're just going to focus on the gas pedal and the brake for a while. All right, but that is an intro to this next one right here. Oh, that's nice. Okay. Right. Oh, wait a minute. No, I skipped one. There you go. Oh, here. Right, so can you guys see the speedometer needle moving? Right there. Right now, if it's not moving, it's just pointed like 55 miles an hour. That's not accelerating, right? That's zero acceleration. That's just like feels like you're sitting in this room, right? You know, little vibration, right? But if it's on the move, right? Suppose you start from rest. How fast are you going after 2 seconds? 12 miles an hour. After 3 seconds, 18 miles an hour, right? After 10 seconds, how fast? Back up to 60 miles an hour. Right? Now, miles, hours, that's good for like American concept, American units. But okay, miles, hours, hey, hours, that's a time unit. Seconds is also a time unit. Right? And we're not going to use miles per hour so much in this class. We're going to use what per what? Meters per second. Hey, if I have meters per second per passing second that something is changing, can you consolidate those 2 seconds, meters per second, and call that what? Meters per second squared, meters per second squared. Consolidate those two, combine those two, right? Meters per second squared. Guys, if you ever want to describe the rate that something is changing its velocity, like speeding up or slowing down, you can quantify that in meters per second squared. Right? You'll never see this on a unit here. Right? Or the opposite, right? If you ever see meters per second squared, that's some kind of description about how something is changing its velocity, right? All right, let's go. How fast? Just in time. I bet somebody knows it. What's the answer? Free fall on Earth. How much does it pick up every second? I know somebody knows. Wait, did somebody have a more precise answer? You guys say? There you go. I knew somebody to do it. Yeah, 9.8 meters per second squared. Yeah.
So when for acceleration, you always see meters per like I haven't seen meters per second over 1 second. Could you like to simplify that? Could you do meters per second squared?
Yeah, that's what we're always going to do. There you go. There you go. Yeah, meters per second squared. There you go. Yeah. Very often in this class, I'll round gravity to exactly what he asked there, about 10 meters per second squared. That's true on Earth. All right, so that means every second it picks up another 10 meters per second as it's falling, right? You guys get that? Okay, I'm gonna skip the next one where he kind of talks about that more. Let's go to how far. So he's talking about how fast. Let's go how far. Here's what I do just to beat the bell. I'm going to skip through this one a little bit. He does a derivation to tell you how far something goes. If you want to say, hey, how far did something fall after so many seconds of falling? He's using d for distance. I usually use x or y, right? He's going to derive it one way. I'll show you guys a graphical solution another day. But look at that. He's getting distances 1/2 gt squared, some version of that. Okay, let's do one more. We'll fit in right before the bell here. Okay, you guys follow that, right? So just off screen here says like distance equals like how far did it fall as a function of time. You release it from rest, right? And so 5 seconds of hell, 5 squares 25, that's square seconds. Right? Got 10 meters per second squared, divide by 2, put it all together, you get 125, and the unit is meters, right? Right, so back over here, right before you guys take off. Now this is not pure free fall. It's like on an incline. We'll discuss that a few weeks from now. Like what was I saying? Like this isn't a vertical wall. Like wee. But I bet this motion is really related to that. I mean, this is being pulled under the influence of its own gravity, a lot like something that's like pure free fall, right? Right. So I bet a lot of your results from this lab are going to maybe correspond to some more generalized equation that you have. Again, this is the set of experiments that Galileo was doing. Galileo would roll balls down the inclines, and that's like a slowed down version of pure free fall. So there's a lot of similarities. It's like just like a slow motion version of it. Okay. Oh yeah, you did beat the bell. Right, you guys got any questions for tomorrow? All right, so again, tomorrow I'll have you guys at teams. I'll put a card on your desk. I'll have this up here so you guys know exactly what experiment you're doing. You guys are going to take your table and figure out which variables you're going to measure. All right, you guys have a great afternoon.